Okay, last time I got cut off about 30 seconds before I actually wanted to finish. So let me just finish up on 58 and then we'll move on to the end of section B2. No matter what you do to calculate, as long as you do the right thing, you should get an answer of about 1.52 for the index of refraction of medium X. This does not necessarily correspond to anything on the reference tables. It doesn't have to. There are plenty more materials that light could travel through other than the ones that are on the reference table. Let's just make sure it makes sense. We have studied, we know that when light travels from a higher index to a lower index, this medium X, has an index of refraction of 1.52. Going to air is an index of refraction of 1. We're going from high to low. We know that that should make the light bend away from the normal line, and that does in fact happen. So our answer does make sense. It's a good thing we did not get an index of refraction less than 1 because that is physically impossible. That would imply, if you do a couple more calculations, that light in that medium is traveling faster than it does in a vacuum, which is impossible. So it's good our answer makes sense. To move on to questions 59 through 60, we'll go all the way up through 65. So 59 to 60 is a kinematics question, fairly straightforward, free fall question. On the actual Regents, I saw most people handle this with little to no problem. A student wishes to record a 7.5 kilogram watermelon, that would be the mass, 7.5 kilograms, colliding with the ground. Calculate how far the watermelon must fall freely from rest. From rest is important, that's the initial speed. So it would be traveling 29 meters per second, final speed, the instant it hits the ground. And please notice fall freely. One of the things that you need to remember, if something is in free fall, it means that acceleration is 9.81 meters per second squared, and I'm going to write toward the ground. Toward ground. So to make this easy on ourselves, we might as well pick the direction toward the ground to be positive. So I'll write down is positive for this one. We know the initial speed is 0. We know the final speed. And we know the acceleration. We are just looking for the distance. That's where it says how far. So VI, VF, A, and D. That leads us to the kinematics equation that looks like this. VF equals VI squared. VF squared equals VI squared plus 2AD. Notice that our equation does not include the mass. Free fall, kinematics, we did not even talk about mass by that point. Mass does not affect objects that are free falling. Okay? You can drop two different objects with different masses, they will free fall at the same rate. If you know the acceleration in kinematics, the mass does not matter. Okay? The mass is useful for figuring out the acceleration. But in this case, in free fall, we already know the acceleration. The mass is irrelevant. Okay, we know the initial velocity, getting back to the problem, is 0. We know that this is 29 meters per second squared to 9.81 meters per second squared times d. If we solve for the distance, we should come up with an answer of approximately 42.86 meters. This is how high the watermelon has to be in order for it to have that speed when it hits the ground. Okay? 61 through 62 is an interesting question because it's the first time they've done a momentum question like this, I think, in a while. So it says, as represented in the diagram below, block A with a mass of 100 grams slides to the right at 4 meters per second and hits stationary block B with a mass of 150 grams. Okay, notice they give you those masses in grams, something we don't normally do. After the collision, block B slides to the right and block A rebounds to the left at 1.5 meters per second. In order to neglect friction, calculate the speed of block B after the collision. Show all calculations. Okay, so just the standard do your work. All right, so we've got something that we've got to talk about here. Okay, we have a collision. That's usually a dead giveaway. We're talking about momentum. So we bust out this equation. P before equals P after, or as I like to say, Pi equals Pf. Now the way we have done this all year is we start with, is momentum conserved? This is a collision, there's no outside forces acting, so it appears that momentum will be conserved, yes. Pi equals Pf, okay? Now we've got to break down, well, how many objects are we talking, both before and after the collision? Well, we have A and B before, we have A and B after, they don't stick together, so I'm going to write down P1I plus P2I, the momentum of object 1 before the collision plus the momentum of object 2 before the collision, equals P1F plus P2F. Oh, we should also indicate a positive direction. Just to make it easy on ourselves, let's have it be the direction that A is moving initially, to the right. So I'm just going to make a little notation that right is positive. Okay? So right is positive. Now what we're going to do here is, we're not told the momentum, but we do remember that momentum is equal to mass times velocity. So we're going to split this into mass and velocity instead of just talking about momentum. So if I do that, I would have the mass of number 1 times the initial speed, initial velocity of number 1, plus m2 v2I, mass of number 2, times the initial velocity of number 2, equals m1 v1f plus m2 v2f. Now remember at the beginning, this all looked very intimidating to you. All we were doing is getting more and more specific so we could actually plug things in. Now, we're basically ready to plug in and solve, okay? If you were to just jump to this, that's fine. I kind of like scaffolding it like this to remind you of why we have this equation in the first place. Because this equation is not necessarily true for every single situation, every single collision you might see. So, when we're plugging things in, we have a choice to make, okay? You'll notice that, remember that we said that we were given everything in grams. That's super weird. We don't usually give things in grams. However, we're looking for a speed, okay? If I have grams here, grams here, grams here, and grams here, it's okay, as long as I'm not mixing grams and kilograms together. What I saw with this question a lot when I was grading was people who tried to go from grams to kilograms and went the wrong way. They said 100 grams was 100,000 kilograms. That doesn't make sense, okay? 100 grams, you know a gram is like a paperclip. 100 paperclips is not equivalent to, let's see, a kilogram is about the mass of a textbook. 100 paperclips is not equivalent to 100,000 textbooks. Clearly they went the wrong way, but they didn't think about it. You could convert the right way, in which case this would be 0.1 grams and 0.15 grams, or just leave it, because they're going to cancel out. Let's try the leaving it part. So block A, 100 grams, 100 G, initially sliding at 4 meters to the right, and we said right is positive, so I'm going to do 4 meters per second, excuse me. Now, B is initially stationary. I'm just going to get rid of this term because I know that V2I is 0. That will make this entire term 0. The mass of block 1 is still 100 grams. We do not know, or no, we do know the speed of 1 at the end. It is 1.5 meters per second to the left, so we need to put a negative sign in, plus 150 G's V2F. What is the final speed of block 2? Okay? We do some calculations. I get 400 equals negative 150 plus 150 V2F, and I solve and I see that V2F, the final speed of block number 2, or B as they call it, is 3.66 meters per second. And because it's positive, this was not asked in the question, because it's positive, we know that this is to the right. Okay, so B ended up moving to the right in order to conserve momentum. There is question 61-62. Again, a 2-point question. You get some points for just setting it up correctly. You get another point for having the right final answer. 63 through 65, the last questions in this section. A 1.2 times 10 to the third kilogram car. Now, let's get that out of scientific notation. That would be 1,200 kilograms is the mass. Is traveling east at 25 meters per second. The brakes are applied, the car is brought to rest. So this tells us that V final is 0 meters per second. The initial speed is 25 meters per second east, and it does this in a certain amount of time. We want the total impulse applied to the car to bring it to rest. Now, on the multiple choice section, we talked about how work is the change in energy. Okay? How if you knew the work, you know how much the energy changed. There was a similar thing in the momentum unit. Impulse was the change in momentum. You were given this equation in the reference tables, and since you also know that momentum is equal to mv, you should be able to lead yourself to this equation. M delta v is equal to j. This is the reason I don't have the delta out in front is because we know the mass is going to stay the same. Okay, the mass of that car is not changing. It is the speed that's changing. So if you want the impulse, I think you should write like this. I think you should do Vf minus Vi. Oh, since this is momentum, we do have to pick a positive direction. Let's make east our positive direction. That's the direction it was traveling in initially. If you remember that impulse is equal to a change in momentum, this is a very, very simple question. You know the mass. You just need to determine the change in velocity. At the end, it's not moving. In the beginning, it was moving 25 meters per second to the east. All you have to do is solve this equation. Turns out the impulse acting, I'll even fill that in. Impulse. It's change in momentum. The impulse on this car is negative 30,000 kilograms times meters per second. Okay? That is the, well, that's not really the magnitude. The magnitude is just 30,000, but they're not going to mark you off for having a negative sign there. Technically, it would be more right if you didn't have a negative sign, but that's not a really big distinction because they're just looking for magnitude. Okay, so that is the magnitude. Now, because you get a negative sign, what does that imply about the impulse? We said east was positive. You get a negative sign, therefore the impulse must be directed to the west. The direction of the impulse applied to that car is to the west. Okay, so there is 63 through 64. Let's see here. Okay, so there's 63 through 65. That is the end of section B2. We're on to section C.